Okay, folks, so here we are with clean board for the next segment. And as I said, this one is going to be looking at thermal equilibrium. What happens when we get there? So here's the question. I have two chunks of material. Let's say two solids. I bring them, and there are two different temperatures. I bring them into thermal contact. What's going to happen at thermal equilibrium? Remember, entropy is going to move heat from the hot side to the cold side, right? That's a spontaneous process that occurs because entropy likes it to happen. The entropy at the end is larger than the entropy at the beginning. And that's what drives these processes that occur spontaneously. All right, so again, we have two chunks of material, A and B, and we bring them into thermal contact, right? So that thermal energy, Q, can be exchanged, right? And we know, right, that Q is going to go like that, from the hot side to the cold side. So that in the end, we're going to have A and B, but they're going to be both at some equal final temperature, right? So how do we get what that final temperature is going to be? Now, you already know the answer to this for, say, a simple case. Let's say we have two objects that are the same material, the same, like chunks of iron. And let's just, for giggles, say they're the same size, right? Maybe 10 kilograms of each. One's at a hot temperature, one's at a cold temperature. We bring them together, we let them reach thermal equilibrium, we isolate them from the rest of the universe, from the rest of the environment. They're all by themselves in a thermos bottle. Well, you know, if these two have the same size, in the end, the temperature is going to be halfway in between the two beginning temperatures, right? You know that. All right, so what we're going to do now is turn that, I know that, into let me show that. All right? And the way that we're going to do it is conservation of energy. Because, right, we have Q plus W, right? Because we're going to isolate this system, the only thing that can move around is heat. And in fact, however much heat leaves here, Q out, has to be the same amount that goes in this piece, Q in. Right? If there was more Q that left here, that's just energy. 20 joules leave the hot side. 10 joules enter the cold side. Where did the other 10 go? It couldn't have escaped into the universe. If it went back into the hot side, that meant only 10 left the hot side. So what leaves the hot side has to be equal to what enters the cold side. All right, so I can just write that down as Q out equals Q in. All right, so I'm going to go with this like this is a solid, but exactly the same thing occurs if it was a liquid or if it was gases. All right? What I'm going to do is use the idea of specific heat and put it into this equation. All right? Specific heat, linear relationship with temperature, dependent upon the amount of material. That's really the key here, as you'll see. And so whether it's solids, liquids, gases, whether I use specific heat for solids and liquids, or I use specific heat at constant pressure or constant volume for gases. It really doesn't matter. All right? So, with that in mind, remember what Q is, right? Q is going to be, from over here we see that's the mass of A, right, times the specific heat of material A, all right, times, well, let's see, it's going to go from hot to final. So that's going to be TH minus T final, all right? So that's delta T. So here we have the heat that flows out of the hot side, right? That has to equal the heat that goes into the cold side. So we're going to say it could be a different mass, call it M sub B. Could be a different material, let's call it C sub B, the specific heat for that material type B. Now, times the temperature difference, right? And that's going to be T final minus T sub C, all right? And the reason for it being this way is I want both of these heats to be positive, right? The outflow, the inflow. In is usually positive and out is usually negative, right? When we look at something like this is being done to the system, right? So what I did was just flip the sign on the outbound, right? It should be final minus initial, but that's going to give me, oh, it's going out with a negative sign. So just so I don't have to worry about signage, I flip this. If you want, you could say the change, the Q out plus Q in has to equal 0, right? And now you'll get a minus sign as compared to the plus sign that's sitting here, right? And then you would use the proper final minus initial on this. But what I'm looking for is I know I want them both to be positive numbers. So here's the way that'll work. All right, so now that we're sitting like this, it's going to be simple to figure out the final temperature. Now it's just a little bit of algebra, right? So multiply this out, M sub A, C sub A, TH, minus M sub A, C sub A, T final, equals mass of B, its specific heat, times its final temperature, minus the mass of B times its specific heat times the cold side temperature. All right? And so what I'm going to do now, let's see, I will move this over to here. I'll move this term over to there. So I'll get MaCaTH plus MbCbTc will equal, well, the MbCbTf is still there, and I move this over then. So that's plus MaCaT final. All right? Factor T final out and divide by what's in the parentheses. What I will get then is that MaCaTH plus MbCbTc divided by mass of B, Cb plus mass of A times its specific heat will equal T final. That's it. What does it say? Right? Does this make sense? Well, let's step back a little bit. Right? Let's say that the two materials are the same kind of material. Right? They're both iron. Right? We've talked about them both being iron before. Then the specific heat of the A side is the same as the specific heat of the B side, because they're both iron, right? If I do that, right, then what I'll end up with is, look, there's a specific heat in each of these, so you can factor and cancel out. So I will get, right, the mass of A times the temperature of the hot side, plus the mass of B times the temperature of the cold side divided by the mass of the hot side, the mass of the cold side will equal the final temperature. What is this saying? This is saying that we have like a mass-weighted temperature addition going on here, right? The more of A there is, the more hot matters, right? The more B there is, the more cold temperature matters, right? And then finally, to do this sanity check, let's say both sides are the same size. That's what we started off with, right? We said if we have two chunks of iron that are 10 kilograms apiece, and they're at two different temperatures, what's the final temperature? Okay, two chunks of 10 kilograms each would mean that the mass of A and the mass of B are the same. Factor them out, because they're going to be, just call it M. So factor M out, right? And then look, here's two M's down here. So I will get, in that case, TH plus TC times M over 2M equals T final. The M's cancel. They go away. See, it's nice here I can just erase them because you've got plenty of time to go back and forth seeing what I did. And look, just as you suspected, right? If the hot side is 20 degrees hotter than the cold side, then we put them in thermal contact. In the end, the temperature's in the middle, 10 degrees different. It seems to make sense. And in fact, this is exactly how you do this. If you have two things that you bring into thermal contact, how do you figure out what the final temperature is? Right? You can't just say, oh, size of the thing times temperature plus size of the thing times temperature divided by the total size. No. Because the heat is really what matters. And Q depends upon the specific heat of the material. So it's not just mass times temperature. It's mass times specific heat times temperature, plus the other mass specific heat times temperature, divided by the total mass specific heat quantities. All right? So this is the way to figure out that thermal equilibrium temperature. Again, if this was gases, we have two bottles of gases, right? Which are A and B. And now what we do is we put a little pipe between. Let them mix, right? Let them have fun together. Eventually, at thermal equilibrium, the really fast, really lots of moving particle here, and the slower guys that don't go quite so far, they exchange energies through elastic collisions. Right? Eventually, they come to thermal equilibrium where all the particles now, on average, look the same. What's that final temperature going to be that represents the average motion, random motion, thermal motion of the particles? Same deal as this, right? That the only difference is, remember, for ideal gases, we've got to know, is it a constant pressure or a constant volume process? So that we can know which specific heat value to use here. You can see, in this instance, we have to start off maybe with both of them at the same pressure. So that when I open them up, they stay at the same pressure. Because look, do the volumes change? I'm going to leave you to think about that. It should be one of the things that I've asked you to do for Master in Physics, for one of the last Master in Physics. So now that we've looked at more of these thermal processes, right? The first part was about figuring out specific heats for ideal gases. We got that. There are two flavors for that. Constant pressure, constant volume. Okay? And we even figured out what they have to be. 3/2 kT, I'm sorry, 3/2 K, 5/2 K. Here, we looked at thermal energy, right? How do we reach thermal equilibrium if we have two different materials? We figured that one out. The final chapter in thermodynamics for us is let's use our ideal gas as a heat engine material. We're going to do these thermodynamic processes to move heat through the system and in the process be able to do work. All right? And so that'll be the next segment that we'll look at. Great.